And the correct answer is B. The energy would increase because it takes energy to push this charge against the field. Kind of like you're pulling a sled to the top of a hill, or you buy a lift ticket, you take the ski lift to the top of a mountain. And fields always flow from higher energy to lower energy. So in this case, we're lifting this charge against the field there. So we're storing up electric potential energy. Next, we have a second concept check question to test your understanding. And this one's similar as before. Imagine moving a positive charge against an electric field. And the question reads, if it takes 2,000 joules of work to move the charge, A, how much energy does a charge gain? And then B, how much work does a field do to move the charge back to the right? In this case, let's give you guys a free pass and kind of break it down for you. So first part of the question is, it's just how much energy is charge gained? Well, just like before, if you're pushing it up this hill, you're storing up potential energy. So in this case, we're storing up 2,000 joules of positive energy because it takes positive work to lift this charge against the field there. But in part B, how much work does the field do to move the charge back to the right? The field doesn't have to do any work because in this case, once you let go, the charge naturally wants to move with the field. So you can think of it like, once you go to the top of a sled hill, and you let go, you naturally want to go down that hill. So in this case, it would be negative 2,000 joules. Negative work is done by the field as that energy is released and the charge speeds up, it gains kinetic energy. So now we're ready to break down this big fancy idea called electric potential. It's got a very fancy sounding name, but you've heard of this before because of the term voltage, named after Alessandro Volta, the father of the modern battery. So electric potential has a very specific definition. The equation is V, which stands for electric potential, is equal to PE, which is the energy, divided by Q, the amount of charge that we store up that potential there. And technically, voltage is a difference between 2 points here. So technically, it should be delta V equals delta PE, the change in that potential energy. A lot of times we'll just simplify it and drop the deltas when we're writing it out there. So electric potential is measured in volts in honor of Alessandro Volta, and then energy is measured in joules, metric unit there for energy, and then finally charge is measured in coulombs, named after Charles Coulomb there. So analogy that'll be helpful, since this is very abstract, is to think of voltage, electric potential, as the height you are on a hill, like when you go sledding or skiing, or water pressure is a good example here. So in real life, anytime we have a system of water flowing, so for example, when you have water to your home, there's usually a water tower that a pump lifts the water to the higher potential to create water pressure. So that way, as you turn on your sink, you flush your toilet, etc., water can flow to your homes, except, in real life, you wouldn't just have the water pump back to the water tower. You'd send it to a sewage plant, etc. there. But it's a nice analogy. So that's a good way to look at voltage. It's like electric pressure. We lift electric charges to a higher potential in an electric field, and by doing so, we can store energy inside that field. Another way to look at electric potential is to think of voltage as energy density. So for example, you can think of the density of styrofoam or wood versus like lead. Like styrofoam and wood would float in water, but not lead. Even though you could have a huge chunk of styrofoam, it's still going to float because it's less dense. So voltage is this energy density in an electric field. So electric potential we measure in volts rather, and it's a joule per coulomb. So for example, what do you mean by a 12-volt battery? So car batteries are 12 volts, a little higher technically, but we'll just round it off to 12. So what does that mean? It simply means that for every coulomb of charge that flows through a battery, we give it, by definition, 12 joules of energy. So it's a way to standardize how we power our electrical devices. So what's weird is 12 volts is not a lot, but in real life you want to be very careful if you ever have to jumpstart your car in the wintertime, because even though a car's battery has very low voltage, it could be dangerous because car batteries technically have a lot of charge in them. They have a lot of energy. In other words, they have a lot of what are called amperes, current, amps, anywhere from 5 to 600 cold cranking amps or more. So voltage is not the same as energy. It's energy per charge. Check your understanding in terms of the units. So here we have coulombs, joules, and volts. And let's see if you can figure out how they match up in terms of units when it comes to electricity and energy.